time, we were talking about trigonometric integrals. We completely discussed products of sine and cosine, and now we're dealing with products of secant and tangent. And as I mentioned, there are several cases. We actually analyze easy cases. Let me highlight these identities, which are the ones that are going to be used throughout. Okay? Look. So remember, the way to think about this is that the first one, 1 plus tangent squared equals secant squared. That's a way of turning secants into tangent. And the equivalent form is a way of turning tangents into secant. And this actually tells you that you will need the powers to be an even number. Okay? Because you can always get this square to show up if your power is even. Then, of course, the formulas for derivative of each of these, which we're going to need them in case you want to do a substitution. And just to remember, what's the integral of tangent and the integral of, I didn't write the integral of secant here. Oh, yeah, it is. And the integral of secant, which is ln of secant plus tangent. Okay? All right, so we saw the easy cases, which is when the power of secant is 2. Okay, if the power of secant is 2, that's a pretty easy case. Just let u equals tangent, and your du is a secant square, so you're good to go. And also, another easy case is when the power of tangent is 1, because we use the fact that the derivative of secant is secant tangent. So you take this tangent together with another secant, that will be your du, and then your power is reduced by 1 in the secant, you make your u sub. U equals secant. So those two cases are pretty straightforward. Now, how about other combinations of powers, okay? So let's see what we have so far. So we analyze what happens when the power of secant is even, other than 0, and the power of tangent can be whatever you want. And what was the strategy in this case? So we separate the secant square, that way we can make our du, and then the remaining secant is still even, so you turn it into tangents, and then you make the u sub u equals tangent, okay? That was a strategy in that situation. And that's it. We stop right there. So let's continue with this. Do you have any questions before I proceed? I was giving you an overview of the stuff that we did last week. Okay. All right. So we have seen what happens when m is even, and the power of tangent can be whatever you want. All right. So let us now take a look and see what happens when the power of tangent is odd. Okay. We're gonna cover the case of m being odd as well, but we have to do this in steps. Okay, so we did n even, different than 0. Now, number 2, let's do n odd. So remember, n is the power of tangent, okay? And when the power of tangent is odd, there are several subcases that we need to analyze. Let's deal with the case when m is equal to 0, meaning there is no tangent. What do we do? There is no secant, so what do we do in this case? So, for example, tangent cube, and then another example would be tangent to the 5th. This is the type of problems that we're dealing in this particular case. So the power of tangent is an odd number, and there is no secant involved in here. Okay, so how do we do this? So let me illustrate the idea. For example, I'm going to do it with part A, and then you're going to see. Actually, I'm going to do it with part. Should I do it part A or part B? Let me do part A first, so you get introduced to the technique. So solution. So let's do A. So what can we do here? Okay, so we're going to take advantage of what we already know. Let's try to reduce this to the easy case. So the easy case is, let's try to bring a secant square into the picture. And how can we do that? Well, tangent cube, I can go ahead and take out a tangent square. Because the power is odd, that means that whatever I have left is still an odd power. Okay, keep that in mind. So why is this helpful? Because now this tangent square that I took out, I'm going to turn into a secant. Okay, so we can turn this into secant. That's secant square minus 1. And now we have tangent multiplying secant square minus 1, so we can distribute this. And we get tangent times secant square minus tangent. And notice that now we're going to get two integrals. The first one is an easy integral because you have the secant square. And the second one is, again, the integral of a tangent with an odd power, but notice that the power got reduced by 2, so now it's simpler. We started with a tangent cube, now we exchange it for a tangent only. And now we know what to do because we know the integral of tangent. Now, for example, when you do tangent to the fifth, what's going to happen? You play this game, you're going to have a tangent cube here. And you do it again, and then you get tangent, and then you're done. Okay? So basically what we're doing is reducing the complexity of the integral 2 by 2 at a time, by reducing the power by 2 every time that you do this technique. Okay? So the higher the power, the longer this process will be, but eventually will stop because you're going down by 2 every single time. All right, so now it's easy to see how to finish this. So we have two integrals here. And then the first one, remember, in the first one, what is it that we do? So we can actually do it right now, we can do it in our mind, right? If u is tangent, then u is secant squared. So this is going to be u squared over 2, so that's tangent squared over 2. You see it? So again, if you want in your mind, just think about this. This is your u, right here is your du. So the integral is 1/2 u squared, so that's the same thing as 1/2 tangent squared. We okay with that? Minus, and then what was the integral of tangent? Natural log of secant. Remember, if you don't remember, what you do is write tangent as sine over cosine, and then you make a u sub. U equals cosine, and then your du pops up, etc. So minus natural log of absolute value of secant. Or you can bring this minus in and then put plus ln of absolute value of cosine. That's also the same thing. Okay. All right. Questions about part A? No? All right. So about B. Let's see. Do it. Do tangent to the fifth. Put this technique to good use. And remember, be smart. Once you get your tangent cube popping up, you already know what the integral is. You can reuse part A. So you don't have to compute it again. You already computed that. So once tangent cube pop up, just stick in there the answer. So this is a typical technique when you're doing integrals. But maybe you cannot solve it in one shot, but you make it simpler. And then you continue doing this until eventually you are done. Okay, so let's see. What do we do here? What do we need to do? Why just one tangent? Remember, the idea was to separate tangent square so that we can get a secant square out of that. So you take out a tangent square, right? You take out a tangent square, so that means there will be a tangent cube times tangent square here. But remember, there's a reason why we're taking out this tangent square. Why are we taking this tangent square out? So we can turn it into secant. Now we can turn this into secant square minus 1, right? The point is that now when you distribute, you will get two integrals. The first one is the easy case that we can do easily, u equals tangent. And then the second one is equivalent to the original one. It's just that it's simpler because instead of 5, now you have a cube. So you reduce the power by 2. And then the idea is that now you do it again, right? But there's no need to do it again, you already solved it. So now we just copy whatever answer we got from above, okay? But you can imagine if instead of 5 you have 7, tangent to a 7, what do? Same thing, it's just that then you will get a tangent to the 5, and you do it again, you get a tangent cube, you do it again, you get a tangent, and then you're done. Yes? Okay. So let's finish it. So this would be then tangent cube times secant square of x minus tangent cube dx equals 2. All right, so let's do the two intervals. Let's see the first one. Do you see the u sub? U equals tangent, the u secant square, so this will be tangent to the 4 over 4. Is this okay? Think about u to the 4 over 4, but u is tangent. I'm doing like that because you write u equals tangent du, then making it too long for no reason. So tangent to the 4 over 4 minus, and then we need to put the integral of tangent cube. We already did it, so I'm just gonna copy the line from above. So minus 1/2 tangent square plus ln. I'm distributing the negative. Absolute values. Okay. What I did here was I just copy stuff from above. So this is from above, from part A. Questions? Yes.
So I understand why in u sub u is tangent because when tangent has a higher exponent, it'll be easier, whatever. But in part A, where it's just tangent secant squared, can't u also be secant? Because,
yes.
But then you would get half secant squared.
Like
it would give you.
So what do you get? Tell me. That's a good question. Ask it.
Yeah.
Finish it. So finish your question.
So then if you were to do that integral, then you would be secant, right?
Yes. You do secant tangent. Yes.
So then you would get half secant squared x.
Okay. So you're wondering how is that the same as what we have here?
Yeah.
Okay. What is secant squared? So imagine that you have here half secant squared, right? What's secant squared? So that would be tangent squared plus 1, right? You distribute. So you get your 1/2 tangent square, and then you get a plus 1/2 floating around, but you can put it together with the c. Remember, this c is an arbitrary constant. So if I want, I can come here and right now do this. And there's nothing wrong with doing this. Right? This is the same answer because c is just any constant. So this is just a new c, for example. Right? So the difference between tangent square and secant square, they differ by a constant. Right? So what's the difference? The difference is what is it? So tangent square minus secant square equals -1. So the other way around, if you want secant square minus tangent square equals 1. So that difference is absorbed by this constant c. So whether you have secant square, tangent square, it doesn't matter in the answer. Because the difference is a constant and it's being absorbed already. Good question. And yeah, you have to be aware of that because you may get secant, but then if the answer says tangent, then you're like, okay, what's happening here? Well, you need to know that the two things are the same. Now, if it was a definite integral, if we had limits, you get the same number regardless. So then there's no confusion. But when the integrals are indefinite, this kind of stuff might show up. And this case is easy. Sometimes it's actually not straightforward to see the equivalent expressions. You get something, then somebody else gets something else. They look completely different. And you have to do something super, sneaky and whatever to show that the two things are equal to each other. It's not always that straightforward. But yeah, here it doesn't matter. Good. Okay, any other question? Okay, good. So this is what we do when the power of tangent is odd and there is no secant. Okay, so now let us talk about what do we do when there is a secant. So that was case 2.1. So the power of tangent is odd and there is no secant. Now case 2.2, what do we do when the power of tangent is still odd, but now there is a secant with an odd power? I remind you that we don't need to consider the even case because we already did that. We already discussed what happens when secant shows up with an even power and tangent is whatever you want. Okay? We already discussed that. So the question is, what if secant shows up with an odd power? Okay? So that's what we're doing now. So m is odd, but we have tangents. And then the next case would be, what if we don't have tangents? What do we do? Okay? That's a different story. It's a different technique. All right, so let's say m is odd, and actually, also it could be even, it doesn't matter, or even, but there has to be a secant, so it has to be different than zero. So basically, this just means that m has to be different than 0. But I'm stressing odd because if it's even, it would be in the previous case, and you can use the previous technique. So that means that you can use both techniques that you're about to see, whichever you prefer. Just like what just classmate pointed out, for tangent cube, let's see, for what's here, tangent of x times secant squared, you have two ways of doing it, right? You can let u equals secant, like what we did, or, sorry, u equals tangent, and then you do u secant squared, or you could let u equals secant, and you do u secant tangent. Two ways, right? So, same thing here. Okay, so basically, we are in the situation in which tangent is odd, and there is a secant in the expression. And we are interested what if the power is odd, because the power of secant is even, we know what to do from the previous case, okay? All right, so again, let me illustrate this with some examples. Something like this, secant cube times tangent cube. So, I mean, once I explain this, both odd. Whatever we do here, then it's the same thing if, if you have 5 or 7 or whatever. So it should be more than enough. So let's see. Any ideas? What would you do here in a situation like this? Now, using, the techniques that we have been doing. Yes?
Can't you turn tangent into, or tangent cubed into tangent squared times tangent x, and then you turn the tangent squared of x into secant squared of x minus 1?
How would that help you?
Because then you could distribute it. Then you take away one of the secants and turn that also into there.
Remember, you only have one tangent, so how is that going to help you?
Because then you can use secant as u into du.
Okay. And then the other integral. So let's see. We take out a tangent. What you're suggesting is let's take out a tangent. Then there's a tangent square that we can turn into secant. So when you distribute, you have a bunch of secants, and then you distribute the tangent, and it turns into an easy case. Yeah, exactly. Okay, very good. Yes. Listen, I have something else in mind. So I like that. So let me just think to see if I had something else in mind. So if I take out, taking out secant square is not a good idea. Taking out tangent square, because remember, we are in the case in which tangent is odd. So taking out tangent square will not be good either. So yeah, that's the way to go. So because tangent is odd, okay, remember, we're in the situation in which tangent is odd. Because here, it doesn't really matter whether this secant is even or odd, it's just that we have some secant in here. Tangent is odd, we are going to take out one tangent. When you take out one tangent, what remains is even. So we can turn it entirely into secants. Why is that good? Because then you're going to have two integrals with a bunch of secants, and when you distribute the tangents, you have one tangent only. That's an easy case, because you have your secant tangent, you let u equal secant. Okay? That's the second example of the easy case. So that technique always works. So let's illustrate it in this example. So again, the idea here is that we're going to take out one tangent from here. So in this case, you write it like this, okay? So that would be secant cube times tangent squared times tangent. So we're going to reserve this tangent here for later. Now, the remaining tangent, because it's even now, notice that if it was to the fifth, again, you take one tangent only, then you have to the fourth. That you can turn into secants entirely by doing it square, and using the identity, okay? So the idea is that whatever tangent is left, turn it into secants. So we can do this as secant squared minus 1, okay? So now let's distribute. So we're going to have the integral of, I'm going to distribute the secant only so you can see it. Secant cube minus secant to the fifth minus secant cube times tangent. Okay? And actually, let's be a little bit smarter. Let's separate the tangent, and since we already have a secant, because you see, that's why I'm saying n is different than 0. So that means there is some secant in the expression let's put a secant next to a tangent. So I want to do that as well. So let's do that in one shot. So I separate a tangent, but let's also separate a secant. So this is now a square here. So we are making our preparations, okay? Now we want the rest to just be secants, and we already have that. So let me rewrite this then. So we have secant squared times secant squared minus 1, secant tangent, and we are ready. So we let u equal secant, and du is secant tangent. So we get the integral of u squared times u squared minus 1 du. So this is our du right here. And now this is polynomial. And once again, notice that you can always do this as long as the power of tangent is odd and there is a secant in the expression. Because you can put a secant, put a tangent together, so secant tangent separate, the remaining tangents will be even, so you turn it into secants and then you do your u sub. All right, so this is u to the 4 minus u squared du. So that's 1 over 5 u to the 5 minus 1 over 3 u cubed. And u is secant. So 1 over 5 secant to the 5th minus 1 over 3 secant cubed. So again, I want you to, you could go ahead and try to memorize all the different techniques, but don't do that because there are many cases, right? Just learn to reason. Remember, you can turn, the idea is that you can turn secants into tangent, tangents into secant, but you need even powers to do this. And always remember, derivative of tangent is secant squared, derivative of secant is secant tangent. So always have those u sub in mind, okay? And then, the correct idea should pop up eventually. All right, and always remember that what do? You always try to separate something, a secant, a tangent, or a tangent square, depending what it is, okay? Because then the other alternative would be go ahead and memorize all of these things, but I feel there are too many for you to memorize, okay? It's better to just reason through this and try to analyze. Okay, questions?
Sorry, Professor, I'm just wondering why, when you put the u equals secant x, why is it not like secant squared? Like, how do you know what to make the u equal to?
Oh, that's the technique.
Or secant?
No, secant, because derivative of secant is secant tangent.
Yeah.
You see, that's why we separated secant tangent here.
Oh, okay.
So that we can, when we make u equals secant, the du is already here.
Yes, so if it was, like u equals secant square x.
No, you don't want to do that because then you have to chain rule.
Differentiate secant square?
Of course, and then you have to chain rule. That would be 2 secant times secant tangent.
Okay, it'll make it more complicated.
Yeah, I mean, you could do it, and maybe if you have enough secants in the expression, then you can probably make it work, because that would be what? A 2 secant square times tangent. You can you can separate secant square from here if you want. And then you will have your secant square tangent, right? So you can make it work. But what if you don't have enough power? What if there's only 1 secant here? Then, right? So you don't want to. But this one always works. If there is a secant, you can make it work.
Okay, so
regardless of the power.
Like not square or cube. Like the u has to always be secant to the power 1.
This technique, yes.
And this technique.
What I'm saying is, it doesn't have to be.
Yeah.
Like in this one, you can make a secant square.
Yeah.
Because you have enough secants to cover your du. I don't want to say no, you cannot, because for example, here you can.
It works,
but it doesn't always work.
Yeah.
Okay. For example, if this was a secant square instead of a secant cube, then
yeah, then you can.
But then if it was secant square, you do it another way, right? U equals tangent. The u is secant square, right? Even though this technique will also work, but this is more complicated than just doing u equals tangent in that situation. So you need to understand that all these cases, they overlap in many situations, okay? So you should use the simplest one, okay? All right, I'm just trying to give you techniques so that no matter what integral shows up, you can do it. You look at the powers and then you pick your favorite method to do it, okay? All right, questions on what to do in this combination? So remember, this was the case when tangent has an odd power and there is a secant in the expression, okay? So, okay, so we did that. Then what's left is to discuss what to do when n is even. So what do we do when we have an even power for tangent? So case number 3, what do we do when n is even? And first, let's treat the situation in which there is no secant in the expression. So first, let m equals to 0. Typical examples here are tangent to the 4, even powers of tangent. We already discussed odd powers. How about even powers? All right, so these kind of things. So let's say I didn't put tangent square because how would you solve tangent square? How would you do the integral of tangent square? You are not entirely incorrect. I mean, you are incorrect because you didn't say the correct identity, but your thought process is, well, secant square minus 1. So you have to be careful. Make sure that you need to know the identity. So you have tangent square. How do you integrate that? You can write it as secant square minus 1, right? What's the integral of secant square? Tangent, and the integral of 1 is x. Understand this? So tangent square is easy. So that's why I'm putting tangent to the 4, because tangent square is easy. Does that make sense? Just in case, because I saw some non-believing eyes, let's put it here. So note, integral of tangent square. This can be done easily. All you do is you write as secant square minus 1, and then integral of secant square, that's just tangent, integral of 1 is x. We good? So what do we do? The next case will be tangent to the 4. So any ideas?
What if we put tangent square times tangent square?
Okay, and how would that help you?
Secant square minus 1 times secant square minus 1.
Wait. Don't go all the way to to the secants. But your initial thought was okay. So we take our tangent square, right? That tangent square we turn it into secant. You will have secant square minus 1. When you distribute, the first integral is the easy case because you have your secant square. Your second integral, what is it? It's the same as the original, but the power got reduced by 2. Understand? So it's similar to what we did above with the odd powers. This is basically a reduction process. You reduce it 2 by 2 until you're done. Okay? Good. So the technique here is, let's take out a tangent square. So we take out a tangent square. And why do we do that? Because now we can turn it into secant. That one that we took out, we turn it into secant. Not the other one, this one. Because, for example, in tangent to the 6, you will have a 4 here. You don't want to turn that one into a secant. Okay, you turn the square that we take out, you turn it into secant. The idea is that now you distribute, you're going to get 2 integrals. The first one is easy because you can make a use of u equals tangent. You use your secant square. The second one is equivalent to the original, but the power is smaller. So it's simpler in a sense. So just do the same process again. All right, so from here we get 2 integrals. Tangent square times secant square dx minus the integral of tangent square. Yes? After distributing. Now the first one, who can tell me what's the first one? What's the result for the first integral? Secant cube or tangent cube?
Oh, sorry,
Tangent cube. I mean, again, you could probably separate a secant. No, you see here it doesn't work to separate a secant and a tangent and then make u equals secant. That's not good here, right? You could do that if the tangent was cube, but if it's, odd. But here you do need to make u equals tangent. So this is gonna be tangent cube over 3. And what's the second integral? Well, let's reuse it. We did it already above, right? So we already know that that is equal to tangent minus x, right? So from above, we see that this is, I'm distributing the negative, okay? So this one is from above.
How did you get the tangent cube?
Okay, so this is the same idea that we did in the previous problem above. It's making a little use of. So how would you do this integral? You let u equals tangent, and the u is secant squared. So this would be u cubed over 3, but u is tangent. What I'm saying is, for this kind of stuff, you don't really, I mean, if you want, you do it, but you don't really need to write u equals this because, you know, it's quick, right? Or in general, actually, remember, that was the very first easy case, and we did it completely in general. If you have secant squared times tangent to whatever power, the result is tangent to the n plus 1 over n plus 1. Right? That's basically what we're doing. Okay. All right, so let's see. Go ahead and do, now that we did tangent to the 4, now you can easily do tangent to the 6. Again, be smart and reuse the result. So do tangent to the 6. Remember the technique. Separate tangent square, turn it into secant. So Daniel, as you see, in that case, it was tangent square square, but really don't think about it that way. Think about it as separating, you know, taking out tangent square. Because, for example, this idea would not work. If you write this as tangent square cube or tangent cube square, that's not going to work in this problem, part B. But you can always take out tangent square. Okay, so we get tangent to the 4 times tangent square. Yes? What happens to tangent square? Secant square minus 1. Be careful here, this is a common mistake. Students usually mix this identity and put plus 1 or put 1 minus secant square. So make sure that you understand the identity. Okay? All right. So that's a point which you can make a mistake. So now what do we do after we convert it into secant? We distribute. So we get tangent to the 4 and secant square minus tangent to the 4. So there are two integrals here. Do we know how to do the first one?
Yeah.
So what is it?
E to the 5th over 5. So tangent to the 5th over 5.
So tangent to the 5th over 5. And then minus, what's the other one? Tangent to the 4, but we already have it, so let's put it there. Okay? Again, if you're in the exam and the question is tangent to the 6, right? You have to do the whole thing. You understand this, right? The point is that now you get tangent to the 4, and then you repeat the same process again. And then you get tangent square, and then you do it one more time, and you're done. Okay. So that would be minus 1 over 3 tangent cube plus tangent minus x. Are we okay? So let me say here to remind you from above, from part 8. So if it was to the 8 or to the 10, it's the same idea. A little bit longer, but it's the same idea, right? Let's see, you can probably even guess the pattern. Do you see the pattern in here? So you see the powers are odd. So if, let's say if it was to the 8, tangent to the 8, what would be the answer?
It would be that, and then with a 1/7 times tangent to the 7th x.
So 1 over 7 tangent to the 7, but then you need to do minus all of this. So you have to change the sign. Minus, plus, right? So, and so on, right? So you can actually write a general formula if you want. Do you want to write it?
And I assume if we memorize that, we can't just write that on the test. It says tangent to the 6, we can't just write that answer.
If you write the formula, if you write the formula and tell me, look, the integral of tangent to the 2n equals, because this is the case of an even power, right? instead of tangent to a 2n equals, you write the formula, and then you use it, and I have nothing to say. I mean, I cannot say anything, right? For example, I didn't want you to do that, let's say, in this first exam because I was not there proctoring you, right? I was looking at your face in the camera, for example, but I don't really know what you are on the desk. But right now, the next exams will be here in class. Whatever you do, I know it came out of your head, not from somewhere else. So if you come with a bunch of formulas in your head and you use them, fine, good for you. Okay, that's a. So yeah, you can do that. And in fact, in practice, that's what you do, right? You have the formula there, and then if something pops up that matches the formula, you just apply the formula right away instead of doing this, right? But it's, something more, you don't want to memorize a bunch of stuff. But yeah, do you want me to write the formula? Should we write the formula? Yeah. So note, there is a pattern. Right, so the pattern is if you have tangent to the 2n, right? So remember, this is for even power, so it has to be 2 times something. So what is this? So this is gonna be a sum, right? And okay, so let's put first the big the big expression, and then we write it nicely in a more compact way. And that way you start getting used to it because we're gonna look at series later. And you need to be familiar with the sigma notation anyways, okay? This will be a finite sum. Later we're going to look at infinite sums. Okay, so what's the pattern? Notice that here you have a 6, and then the powers are odd, and you start with 1 less than what you have. So this is going to be 1 over 2 to the n minus 1, tangent to 2 to the n minus 1 of x. Then you always begin positive, and then you need to alternate, right? Then minus, then that would be 1 over 2 to the n minus 3, right? Because you need to do, this is an odd, so as you keep getting odd numbers, you need to do minus 2, minus 2, minus 2, right? If you do minus 1, if I put now minus 1, so 2n minus 2, that's an even number. We are only using odd numbers now, okay? And that denominator always matches the power. And you keep on doing this, and then the last guy is either plus or minus. Then it really depends on n. So in general, we write this will be -1 to the n. So let's see, -1. It depends how many we have. You see, sometimes the tangent is positive, sometimes the tangent is negative, and it depends on n. Like here, n is equal to 2 because this is 2 times 2, and this is negative. Here, n is equal to 3, and this is positive. So it will be 1 less. So it will be n minus 1, -1 to the n minus 1. Or you can do to the n plus 1, whatever you want. Let me do to the n plus 1. -1 to the n plus 1 tangent, and then plus -1 to the n plus 2 x plus c. So basically here I'm ensuring that whatever sign the tangent has, then x is the next one. If this is positive, this will be negative. If it's negative, this will be positive. Okay, that's why I wrote it. Okay, so
couldn't you just have it be n rather than n plus 2?
Yeah, but it kind of feels strange then to write n plus 1 and then down to n. I mean, if you like it more, then we can write here n minus 1, and then we put n here. But it feels weird to have n plus 1 and then let's go back to n. Yeah. Okay, so the nicer format here would be the sum. So let's see, that would be k going from 1. That's 2 to the n minus 1, then 2 to the n minus 3. Okay, so k going from 1 all the way up to, let's see, if I write here, it's probably better to write it backwards. So 1 over 2k, so don't write anything yet. So k going from 1, then 1 over 2k minus 1. It's just that you have tangent x, so this would be, it's a little bit complicated to write it, because you have x and then the other stuff is tangent. So I would say -1 to the n times x plus, and now we can put all the other terms together with the tangent. So wasting too much time. That's fine. Okay, so my index has to be this guy, this 1, the 3, the 4, and so on, all the way up to. So how do you get here? That's 2n minus 2n minus 1. Let's give you 1. So the power here in tangent, so this power here is the same thing as saying that 1, you can think of it as being 2n minus 2n minus 1, right? Because I'm counting like this, so 1, then 3, then 5, then 7, all the way up to this odd number, 2n minus 1, okay? That would be my index. That's the index that I have to keep track of. So k going from 1 all the way up to, let's see, I will change this most likely, but let me just, then I want to say that I'm going to be alternating. I'm going to begin always positive. So -1 to the k minus 1, and then this is going to be tangent to the 2n minus 2k minus 1 of x. Let me make sure that this works, and then if anything, we can find a more pretty formula. It's just that it has to be in terms of n. So let's see, when k is equal to n, I want to make sure that I get my last term. So the last term in this sum is when k is equal to n. When k is n, we have -1 to the n minus 1. So we have here, you have an n in here, and then you have 2n minus 2n minus 1. That's a 1. This is your tangent. This is a 1 down here. So this works. Now, we'll make it prettier than this. So, I mean, you can combine these, and then you can write it as 2 times m minus k plus 1. That's probably easier to remember. 2 times m minus k plus 1. So rewrite it as, and then of course remember plus c. So then -1 to the n x plus the sum from 1 to n, -1 to the k minus 1 of tangent to the 2 m minus k plus 1x over 2 m minus k plus 1, and then plus your big C. Again, I don't see anything worth remembering this. I mean, it's easier, I guess, to look at the pattern on the top, and then you can just use that, okay? But I'm just rewriting this as a sigma notation. Basically, this k is the one that is taking care of doing the -1, the -3, the -5, the -7. That's what the k is doing. But because k is running from 1 to n, that's why I have to do this 2k minus 1 to make sure that I always get my odd numbers. When k is 1, 2k minus 1 is 1. When k is 2, 2k minus 1 is 3, and so on. Okay? So as k goes from 1 to n, this 2k minus 1 goes through all the odd numbers up to 2n minus 1. You can ignore this little discussion. It's probably worth looking at this part over here, up to here, maybe. On this one. Okay? The rest is just how to write it in a more compact way. Okay. Actually, it's a better way of doing this. And let's write it recursively. Do you know what recursive formula is? Okay, so recursive formula, we're going to talk about that when we discuss sequences. It's a formula that uses its own form to be defined. For example, have you heard about the Fibonacci sequence? That's an example of a recursive sequence, because you begin with two numbers, let's say with 0 and 1, okay? And then you define the Fibonacci sequence as follows. The next term is the sum of the previous two. So you need to use elements in the sequence to define the new one, okay? So for example, what would be Fibonacci sequence? You begin with 0 and 1. Then the next term is the sum of the previous two. So the next one is a 1. Then what's the next one? A 2, then a 3, 5, 8, and so on. That's called the Fibonacci sequence. It has to do with the reproduction of rabbits and a bunch of other stuff in nature, okay? So, but this is what would be the recursive definition? You can say, okay, the 0th term is equal to 0, d1 is going to be equal to 1, and then we can define dn as dn minus 1 plus dn minus 2, as long as n is greater than or equal to 2. This right here is a recursive definition. I'm defining the sequence using the sequence, the expression for the sequence itself, right? But this means that you need to know the previous two guys to know the next one, okay? So we can actually rewrite this formula in a recursive way, meaning I'm going to write this in terms of another integral which has a lower power, okay? And what was the idea? Let's figure it out. So remember, so what we do is we take out a tangent square. So when you take out a tangent square, the power is reduced by 2 of the remaining tangent. Then the tangent square is turned into a secant square minus 1. Okay, so if you want, this is the general way that we do this. Okay, instead of showing an example, this is the general way. Now, when you distribute, you get your easy integral, which you can use power rule, right? So that would be, you need to bump the power up by 1. So 2n minus 1 over 2n minus 1. And then minus the integral of tangent to the 2n minus 2. Or if you want, 2 times n minus 1. So this is a cleaner expression. And the idea is that now, notice that this is essentially the same as the original one, because the power is smaller. Now apply the formula again to this one. And then the next term is going to show up. Then apply again, and the other term is going to show up. So you get these terms that we have here. We just roll all of them together, but you're going to be getting these terms one by one showing up as you apply this recursive formula. And this one is probably easy to remember. Okay? By the way, we also have these for powers of cosine, cosine to the n, and sine to the n. They are reduction formulas that you can write down as well. Okay? All right, so enough with this. So the point is that we know how to do tangent to an even power. Okay? All right, now what if we have, so that was when the power of tangent is even and we had no secant. Now, what if we have secant with an odd power? Because remember, even power of secant, we already did that at the very beginning. So 3.2. So that was case 3.1. The tangent of the power of tangent is even and there is no secant. Now, case 3.2 would be The power of tangent is still even, but m is odd. So we have a secant with an odd power. Again, if secant is an even power, we know what to do, okay? That's a previous case. All right, so two situations, 3.2.1, no tangent whatsoever. In other words, what do you do if you have secant cube, secant to the fifth? How do we do that inter? We haven't discussed this, okay? And then, what do we do when we have a tangent in both? The point is, it gets reduced to the previous one. That's why we're doing this. Okay, so example here is secant cube, secant to the fifth. I'm not putting secant because we already know what integral secant is, right? What's the integral secant? No, it's a derivative. Be careful. What's the integral secant? ln of absolute value secant plus tangent. Remember, I told you to remember that integral. It's right here. Integral secant is ln of absolute value secant plus tangent. Okay, remember that because this is going to pop up several times and you don't want to derive that every single time. Okay, remember the trick was, how do we get this formula? We multiply top and bottom by secant plus tangent. And then it turns out that the derivative of secant plus tangent is what you get in the numerator, so that's why it's ln of secant plus tangent. Okay? All right, so we know how to do secant. That's the first case, right? The power odd. So the next case would be secant cube. Any ideas? Okay. Okay, let's see. So we take out one secant. So secant of x times secant squared. And then what do you do? Okay, how would that help you?
So then you turn it into tangent squared of x plus 1, and then you distribute the secant squared, the secant of x.
So you will get secant times tangent squared. How do you do that one?
Wouldn't it just be secant tangent times secant times tangent is the derivative of tangent, and then you would be.
Wait, the derivative of tangent secant squared.
Oh, never mind, I messed up. Too many tangents and secants.
So we get stuck there, okay? Actually, this is done by parts. Okay? So this is done by parts. So let's see, what do you think to be our dv? Remember, the rule in most cases is that dv should be something that you can integrate, but integrate nicely, right?
It should be secant tangent, right?
We don't have the tangent here.
Oh no, I was talking about
No, right here. What should be our dv? Secant squared, because that's the one with the nicest integral. Okay? I mean, if it doesn't work, we just erase. Okay, it's not a big of a deal. But the point is that here it's natural to let secant squared be your dv. So this will be our dv and this will be our u. Okay? So we're gonna do by parts. So by parts, we're gonna let u be secant and dv is gonna be secant squared. So what's du? What's du? Derivative. You take derivative. Secant tangent dx. And what's dv? And what is v? Tangent. And then v is going to be tangent of x. Okay, let's go. So we do uv. So this would be uv. So secant tangent minus the integral of v du. So when you do v times du, you're going to get secant times tangent squared dx. And then you may wonder, well, what's going on? This is the same that we were getting before when your classmate gave an idea of how to do it. But here is a good thing now. Now what we're going to do is we're going to replace tangent squared by secant squared minus 1. Then what's going to happen is that the secant cube is going to pop up, but with a negative. So we can move it to the other side and solve it like an equation. Remember when we did those integrals, like product of, let's say, sine and exponential? That is a cyclic integral that when you use by part like twice, the same integral will pop up and then you solve it like an equation. That's similar to what's going to happen here. We do by parts, then this tangent square, we're going to turn it into secant squared minus 1. So a secant cube will show up again. And then the good thing is that there is a minus, so when you move it to the other side, it doesn't cancel. You collect like terms and then you finish off. So you will see. So you solve this equation like, that's the point. All right, so this is secant tangent minus, so again, what's going on here is that this tangent square, we're gonna write it as secant squared minus 1, okay? So let me put a parenthesis here. Then you're gonna have, when you stay with the secant, you're gonna have secant cube dx, and then minus the integral of secant, right? Because you get secant cube minus secant, okay? Now, well, integral secant, we know what it is. We can calculate this one. And this secant cube, because it has a negative in front, we can move it to the other side and collect it together with the other secant. So we're going to get here, this is equal to, so I'm going to move it to the other side. So we're going to get 2 times secant cube is going to be equal to secant tangent plus the integral of secant, when you with the negative. And what's the integral of secant?
Where did the 2 come from?
You see this guy?
Mm-hmm.
That integral is negative, right?
Right.
I move it to the left hand side. I collect it. That's the same as the original.
Okay.
So that I get the same integral twice.
Oh, okay.
It's like doing I plus I, right?
Yep.
So you get 2I. So we get that 2 times secant cube equals secant tangent plus ln secant plus tangent. And therefore, the integral of secant cube, now we divide by 2, equals 1/2 times secant tangent plus ln of absolute value of secant plus tangent. Did you understand this? Okay, and if it was to the cube, to the 5th power, it's essentially the same thing. You take out secant squared, okay? It's just that you see here, when we did this process, what happened? The secant cube turned into a secant. The power got reduced by 2. When you do it with secant to the 5th, the same thing will happen, but then here you will have a secant cube instead of the secant. Then you have to do it again with that one, and right? So that's why we left it to the end, because this is the one that is a little bit more tedious, because you have to do by parts, and you know. Anyways, do you want to see secant to the 5th, or I mean, we already have secant cube, so we can reuse, right? Let me actually rewrite this without the parentheses and put another 1/2 in here. Okay, just still with the 1/2. Sorry. So for part B, if you have to do secant cube, secant to the 5th is again the same idea. So take out secant square. So split it as secant cube times secant square. And then we're gonna do it by parts. So our u is the secant cube, because our dv will always be the secant square. That secant square that we take out is to make it dv. What is du? What's du? It's gonna be 3 secant squared of x times derivative of secant, which is secant tangent, right? So I have to use chain rule. So du is actually 3 secant cube times tangent. And then our v equals tangent. And you see, that's the point. There is always when you let u be equal to secant to whatever power, when you do the derivative, a tangent always pops up. So because your dv secant square, always your v will be tangent. Then when you multiply the v du part, you're gonna get a tangent square, and then you can turn it back into secant square, and then you go back to the original power, and that's why you can solve the equation back. Okay, so that's why this is always guaranteed to work. So now this would be uv minus the integral of v du. So u times v, so that's secant cube times tangent minus the integral of v du. So that's 3 secant cube times tangent squared dx. What's the idea now? Tangent square, we turn it into secant square minus 1. So let me go down here. Secant to the 5th dx becomes secant cube times tangent minus 3 times the integral of secant to the 5th. I'm distributing the secant cube now. Minus secant cube. And you see what's going on, right? When you distribute this, you have 3 secant to the 5th, then you negative 3 secant to the 5th, the integral secant to the 5th, so you can move it then to the left and collect it with that guy, getting a 4 over there, and then plus the integral secant cube. So you basically exchange the secant to the 5th with a secant cube integral. And now you will have to repeat the process again to be able to do it. But we can reuse our previous work, right? So I will do that. So the point is that here we're gonna get secant cube. So the negative 3 integral secant to the 5th, I'm gonna bring it to the left positive, so you get 4 times secant to the 5th. And then here we're gonna have plus 3 secant cube. So our integral is 1 over 4 times secant cube tangent plus, and now 3 times, and the integral secant cube is what we have in there, right? So I'm going to put 3/2 times secant tangent plus 3/2 ln of secant plus tangent. Plus c. And if it's secant to the 7, right? At least it's super tedious and painful, but you know how to do it. Okay? It's exactly the same idea. Do the same thing, it's just that instead of a cube here, you will have a 5. Right? The coefficient here, notice how the numbers are changing because it really depends on the power. So when you do the derivative, this number has to do with the derivative when you do your du in the by parts process. Okay? All right, questions? And then the last case is one more case that we have not covered, which is what to do when you have an odd power of secant and an even power of tangent mixed together. Okay? So that was already a problem. So tell me more. You mean this one? This?
Yeah.
Do you see here? Are you okay here?
Yeah.
So when you distribute the secant cube, the secant to the 5th pops up again. And this will always happen. Whatever the original integral was, the original secant was, is going to show up again. When it's an odd power, when you do this process, it's going to show up again, and then you solve it. That's why you can solve it like an equation. It looks like magic, but it's not magic. All right, are we good with this? So last one. So we were in 3.2.1. Now let's go to 3.2.2. In other words, remember, we are in case 3, which is the power of tangent is even, okay? And then That's case 3. Power of tangent is even. Now we are in the case of power of tangent is even together with an odd power of secant. We did what happened when there's no tangent, because 0 counts as an even number, right? Now what if we have a tangent together with an odd power of secant, okay? But it has to be even, because odd, we already discussed that above. What to do when the power of tangent is odd. So 3.2.2 is what happens when we have an even power of tangent and different than 0, because we already discussed the equal to 0 case above. And then, of course, the power of secant is odd, okay? So typical examples would be, just gonna do the simplest one that can show up, because any other is exactly the same idea. You're gonna be, if you thought that the previous was painful, this is more painful. Because the idea is that we're gonna turn this into the previous case, and then you do the previous case. Okay, so how can we turn this into a previous case?
Turn tangent into secant, right?
Turn the tangent square into secant square minus 1, distribute, so you get 2 of the above case, right? You get a secant fifth and a secant cube. But the point is that you know how to do it. Okay, so that's the idea. So remember, every time that you have an even power of tangent, you can turn into a bunch of secants. Okay, and then you distribute, and then those with odd powers, you do them. Those with even powers, because there could be even powers, you know what to do. When the power of secant is even, we already discussed that way up. Okay? And that finished all the cases. So the idea is that we turn the tangent that we have, we turn entirely into secants. We can always do that because we are in the case of the power of tangent is even. So just turn entirely into secant. And what happens is that when you distribute, you will get a mix of secants with odd or even powers. The odd powers, we do the previous case, the by parts, etc. The even powers, we do the previous techniques that we have discussed. Okay? Separate secant square, the remaining secant, turn it back into tangent, and then make a little use of. Okay? That's what you do if you had an even power. So, this is secant to the fifth minus secant cube. Right? And then, I mean, we can actually be a little bit clever now because we already did both of these, right? And just put them and subtract. In fact, we can be a little bit more clever in the sense that notice in this line here, right? If I divide by 4, it tells me that secant to the fifth equals 1 over 4 secant cube tangent plus 3/4 the integral of secant cube, which I can then subtract this integral and then just really collect that one. So here's what I'm saying. So the secant to the fifth part, that's going to be 1 over 4 secant cube tangent plus 3/4 secant cube. That's secant to the fifth. But then I need to do minus secant cube. So we can collect those. So 3 over 4 minus 1, that's negative 1 over 4, right?
Professor,
Yes?
why is it 3/4? Because earlier our answer for the previous secant to the fifth was 1/4 times the quantity with 3 halves. So once we multiply.
No, look at the line that I highlighted. I highlighted the previous one. This one.
Okay. All right. Oh.
Right? This one.
Okay.
Yeah. Okay? Yeah, the half comes from integrating the secant cube. The half is part of the integral of secant cube. Because I have not done the integral of secant cube yet, we just have the 3. Okay, and now that we have this, we just put here now the integral of secant cube. What was the integral of secant cube? It's not so hard to remember, so you may want to remember this one as well. Right? It's 1/2 secant tangent plus 1/2 the integral of secant. 1/2 secant tangent plus 1/2 integral of secant, which is 11 secant plus tangent. You may want to remember that.
How would we put that on the test? Would we be like, oh, remember or recall?
If you write it to me, like I said, if you are sitting in front of me, I know that whatever you're doing is coming out of your head. So I don't mind what you do as long as it makes sense. The problem is if you are in your house and you tell me, oh, recall the integral secant cube is this. I'm like, okay, do you really, maybe you had it written on the desk, right? Because you don't show me your desk in the camera, right? So I don't see that. So in the classroom, you are more free, I guess, to do this kind of stuff because I'm looking at you. So, so this would be 1/4 secant cube tangent minus 1/4 times, and then the integral secant cube was 1/2 secant tangent plus 1/2 ln secant tangent. So I guess I'm gonna put here 1/8, and then we just do secant tangent plus ln secant tangent, secant plus tangent. There. And we avoid doing all of those processes. Okay, so now you know, for example, let's say that you needed to calculate this integral in the exam, right? Then it turns into secant to the 5th minus secant cube. You may want to start by computing secant cube first, because then you know that you can reuse that here and play this trick, because then secant to the 5th, you just need to do by parts, but not all the way to the end, because once you get to the secant cube, you collect and use what you already have from before, okay? So you don't really need to compute 2 integrals. Okay? You're really computing one full integral. Okay, with this we're done with all the cases. Now you can do any problem that comes in the homework. Okay, questions? So again, my advice to you is you just need to sit down and do problems so that you can digest all of this. So when you start doing the homework and so on, just have the notes next to you. First, try to see if you can figure it out on your own. Now, in your mind, you already have what's the idea. Sometimes you take out a tangent, sometimes you take out a secant, or a secant square, or tangent square, or whatever, to make the use sub work, etc. If you cannot figure it out, go to the notes, because all the cases are here. Whatever problem you have, try to see what case is it, 3 point whatever, or 2 point whatever, and then look at the technique and you do it. The next one, try it on your own again, and see if you can figure it out. Okay? So, but use the notes, don't ignore it. Otherwise, you're gonna stay forever there trying to figure out the problem. Okay, questions? No? That was 3.2. Okay, so wasted a lot of time in that little formula. That's okay. Okay, I want, let me introduce 3.3. And here I'm just gonna do, so 3.3 is trigonometric substitution. It's just special type of substitution, but this is gonna allow us to deal with some type of integrals. The idea is that after we make the substitution, we're gonna get one of the integrals that we have from before, from the trigonometric integrals, and we already know how to deal with those, okay? Actually, sorry, before I do that, one more example. Because remember that when nothing works, you can go back to the old cases, sine and cosine. So one last example. What if you have something like this? Integral of secant over tangent squared. How do we do something like this? So Giselle, cosecant and cotangent, the idea is that I mentioned last time that secants and the relationship that we have between secant and tangent, we have a similar relationship between cosecant and cotangent, like the identities are the same, okay? They're similar to each other. Therefore, all the techniques that we use for secant and tangent, similarly, you can use them for cosecant and cotangents, okay? That's why I didn't discuss cosecant and cotangents, because identities are the same, but with those two involved, okay? All right, good question. All right, this one. So here, you may want to think about some techniques, but just to do this quicker, sometimes it's easy to just turn everything into sine and cosine. Like this case, it works nicely if we turn it into sine and cosine. So let me put it so you can see it. So remember, secant is 1 over cosine, and tangent is sine over cosine. So this is sine square over cosine square. So when we do the division, this cosine cancel with this one over here, and then that one goes to the top, and basically you get cosine over sine squared. Yes? And what should we do now?
You can set u equal to sine.
Good. So now we just let u equal sine, and we have our du right there, which is cosine dx. So this becomes 1 over u squared du. You okay with this? And now, so how do we do this one? How do we do this integral? What's the technique? Don't forget the basic stuff. And you bring it up as u to the -2, and then we just use the all power rule, right? So it will be u to the -1 over -1 plus c. So that's going to be minus 1 over sine, which is, what's 1 over sine? Okay, let me write it down. What's 1 over sine? Cosecant. So negative cosecant. Interesting. Wait. Negative. So what's the derivative of negative cosecant? So derivative of cosecant, let's make sure that, okay, so derivative, so let's check. So derivative of negative cosecant, the derivative of cosecant is negative cosecant times cotangent. So with the negative, we get cosecant times cotangent. Remember, cosecant and secant, they share similar properties. The derivative of secant is secant tangent. The derivative of cosecant is cosecant cotangent, but you always put a minus. In this cofunction, there is always a minus in there. But now, because of the negative, it becomes positive. So this is cosecant times cotangent. And let's make sure that this is the same thing as secant times tangent squared. So can we see? Let's see, can we do something? So this is, let me turn it into sine and cosine. So that's 1 over sine times cosine over sine. So that's cosine over sine squared. Yeah, this and this. That's like, this guy is the same as this guy, which is the same as this guy. Right? Okay. All right. So, anyways, the point is that sometimes you can just go to sine and cosine. It's just that if you can stick with secant and tangent, it's nice because we can play with the identities that they have. But if you think that nothing is working, turn it to sine and cosine and see if you can do something there. Okay. All right. Well, I didn't waste it, but it's 1:49. Okay, so I think I'm gonna do this on Tuesday, okay? Because I will be rushing it, and there is no point. One last example. Let me just show you a quick example, just to give you a little preview of what's coming in this section. So if you want to look ahead, right, look at the videos and start the homework. So for example, let's do this type of integral. So it's for this kind of stuff. The integral of x squared times square root of 9 minus x squared. How do we do something like this? So now just look at what I'm gonna do on Tuesday. We're gonna do this slowly, okay? I'm gonna explain these things, etc. So instead of doing the algebraic way, which is telling you what substitution will work in here, I'm gonna do it the way I like to do it, because anyways, I'm gonna be doing it later, okay? Just thinking about it. The point is that when you have this, you should think about Pythagorean theorem right away. When you see an expression like this, you should think about Pythagorean theorem. In other words, a right triangle. This comes from a right triangle, in which if I let this theta, my hypotenuse is gonna be 3. One of the sides is gonna be x, let's say this one, and then the other one is that radical, using Pythagorean theorem. Do you see this? I will explain next week how to build this triangle carefully, okay? Just see what I'm gonna do. The point is that the triangle now tells me everything I need to know. For example, now my idea is that I want, instead of x, I want to make a substitution for theta. Okay, I want to go from x to theta. So using the triangle now, I can do many things. For example, the triangle tells me that sine of theta equals x over 3. So that tells me that x must be 3 times sine of theta. The algebraic way is, without a triangle, you need to memorize that in a situation like this, you have to let x be equal to 3 times sine of theta. That's your substitution. But I don't like that. I would rather draw a triangle. The triangle tells me what the substitution is. Okay? The moment that you have x, you can figure out dx. So dx is 3 cosine. Okay? So I have a substitution for x. Therefore, I know what x squared is. I have a substitution for dx. And lastly, I need a substitution for the square root. The triangle tells you. So I can use, what is it? Cosine, right? So cosine of theta is adjacent over hypotenuse. So that means 9 minus x squared equals 3 cosine. Yes? Now we are ready. Let's go back to the integral and plug in. So dx, that's 3 cosine d theta. X squared, that's 9 sine squared. I just squared the x that I have in there. And my square root is 3 cosine. And now we work. So for example, these guys cancel out. So essentially, this integral becomes 1 over 9, the integral of cosecant squared. Okay? Again, we haven't done anything with cosecants, but having cosecant squared is the same thing as having a secant squared. Just remember, the integral of secant squared is tangent. What's the integral of cosecant squared? Negative cotangent, because the derivative of cotangent is negative cosecant squared. Okay? So this becomes negative 1 over 9 cotangent. And now we need to go back to x. How do we go back to x? The triangle. What's cotangent? Cotangent is adjacent over opposite. So that's negative 1 over 9 times square root of 9 minus x squared over x. Using the triangle. So everything, the triangle tells you everything. It tells you what substitution to make, how to make the substitution, and then it tells you how to get back to the variable. Okay? We're doing this next week. I just wanted to give you a quick preview, so in case that you want to dive into it during the weekend or whatever. Actually, not next week. What I'm talking about, today's Tuesday, so on Thursday. For some reason, I thought. Anyways, on Thursday, we will see this.